We're now going to discuss what is arguably probably one of the most important sections in the entire Project Inspector Overview electrical portion, which deals with equipment grounding and bonding and anchoring and bracing of electrical components. It's most important, first off the bat, to understand the difference between grounding and bonding, because they are similar and they are misinterpreted commonly. Grounding is simply the act of connecting something to the earth. The importance is that once something is grounded, no electrical energy may be stored. In fact, it has zero electrical potential if it's grounded. Bonding, on the other hand, is the joining of metal parts together to form an electrically conductive path, the purpose of which is to safely conduct a fault current, and it's going to safely conduct the fault current to ground. All bonded elements have the same electrical potential, and therefore there is no current flow which can take place between any bonded elements, because there is no potential difference electrically. The bonded components, as we've just stated, must ultimately be connected to the ground, so that any fault current that contacts any of the bonded elements becomes grounded, ultimately tripping an overcurrent protection device and stopping the current flow. Project inspectors will also be verifying the proper grounding electrode system and the grounding electrode conductor installations are compliant with the plans and also with the California Electrical Code, Article 250, Part 3. It's also important that we define a couple of these terms. The grounding electrode is a conducting object through which a direct connection to earth is established. This can be any number of grounding electrode systems, either a ground rod, a metal underground water pipe, a concrete encased rebar or copper wire, metal building frame, a ground ring, etc. And all of these different types of grounding electrode systems are discussed in Part 3 of Article 250. A grounding electrode conductor, on the other hand, is an actual conductor. It's a wire. It is not an object. It is a wire that is used to connect the grounding electrode, which is the object, or the grounding electrode system, to the equipment, or to the system grounded conductor. So remember, a grounding electrode is an object that's used to ground. The grounding electrode conductor is a conductor. It's a piece of wire. It's important to make these distinctions because we're going to be discussing these differences in quite a few slides. When determining the proper system grounding, the project inspector is going to be reviewing and verifying several components. One of them is that the grounded conductor, which is the neutral, is brought to the service equipment and grounded. These requirements are found in Article 250.24c. You're also going to verify that the main and the system bonding jumpers are installed appropriately and per the plans. This is identified and detailed in Article 250.28. You must also verify the grounding of separately derived systems. This is found in Article 250.30. And to clarify, a separately derived system is a premises wiring system whose power is provided by sources other than the utility service. For example, a transformer, a generator, a battery, a PV system, etc. Those are all separately derived systems. They also have no direct electrical connection to other supply conductors. We'll now talk a little bit about a variety of acceptable grounding electrode systems. This falls in line with the requirement for project inspectors to verify that the proper grounding electrode system has been installed per the plans and installed correctly. One of these examples is metal underground water piping. That's detailed in Article 250.52A1. Another method is the metal frame of a building or a structure. That's identified in Article 250.52A2. A U-for ground, or a concrete encased electrode, is identified in Article 250.52A3. And as we know, this includes a number 4 AWG minimum conductor by 20-foot long minimum bare copper, or a piece of 1/2 inch by 20-foot minimum rebar. A ground ring is another type of grounding electrode system. It's identified in Article 250.52A4. And this includes a minimum of number 2 AWG by 20-foot minimum bare copper, a minimum of 30 inches below grade. Continuing with more examples of grounding electrode systems, there's rod and pipe electrodes. These are required to be 8-foot minimum in length. Article 250.52A5 describes these in more detail. The pipe type, which is either a pipe or a conduit, is required to be 3/4 inch minimum diameter, galvanized or otherwise protected. The rod type is required to be 5/8 inch minimum diameter, either copper, stainless steel, or zinc coated steel. A single rod electrode must be supplemented by an additional electrode installed 6 feet minimum from the original if the original ground rod measures greater than 25 ohms. The upper end of the rod type electrode must be flush with or below ground. This is a simple diagram depicting the U-for ground, which is very common on projects. This is a standard concrete encased electrode design that's identified in Article 250.52A3, and I'm sure that most of you have seen this example on many projects. So it's basically depicting the fact that the 20-foot length minimum has got to be 20 feet horizontally. There has to be a minimum 2 inches of concrete cover on the bottom, and this can either be a 1/2 inch piece of a 1/2 inch diameter piece of rebar, or a piece of number 4 AWG bare copper wire. Here's a reminder for us. Read and review every word and every symbol on every plan and specification sheet for every project every time. And as you can see, this particular drawing shows 3 separate grounding electrode systems. We're going to discuss these in a little bit more detail, but this is a pretty elaborate setup. This was a pretty elaborate job, and it's interesting that they utilize so many different types of grounding electrode systems in this project, and we'll discuss these in more detail. Here's a blow-up view of the previous slide showing all of the different grounding electrode systems that are being utilized for this project. As you can see here, this is a 3/0 U-for ground at the generator pad. This particular grounding electrode system includes 3 10-foot ground rods at 20 foot on center for the temporary kitchen main power panel. This elaborate grounding system incorporates at least 4 of the main types of grounding electrode systems that we just discussed. They're basically using 3/0 bare copper wire to join this copper bus bar to, number one, cold water pipe, number two, three 10-foot ground rods at 20 foot on center. They're also grounding it to the building steel, and they've included a minimum of three 20-foot pieces of rebar in the concrete footing or foundation. This is a very elaborate and almost fail-safe, I would say, method for ensuring that every conceivable system in the particular building that it's grounding is grounded securely. Now we'll discuss the other main component of a grounding electrode system, and that is the actual grounding electrode conductor, which is abbreviated GEC. And these installations are also detailed in Article 250, Part 3. Grounding electrode conductors are permitted to be made of copper, aluminum, or copper-clad aluminum. The wire type, of course, may be bare, stranded, solid, covered, or insulated. The grounding electrode conductors and the grounding electrode bonding jumpers in contact with the earth do not have to comply with Article 300.5, Table 300.5 cover requirements, but are required to be buried or otherwise protected from physical damage. And this is reiterated in Article 250.64 A and B. It's important to note that aluminum and copper-clad aluminum are not permitted to be in direct contact with earth, masonry, or other corrosive environments. And also, where used outside, they are not permitted within 18 inches of the earth. They are, however, permitted to be installed on or through framing members. Continuing with grounding electrode conductor installation, ferrous metal raceways and enclosures for grounding electrode conductors must be electrically continuous. That requirement is found in Article 250.64E. Table 250.66, which is called Grounding Electrode Conductor for Alternating Current Systems, identifies the required size of grounding electrode conductors for use with service entrance conductors. Ferrous metal raceways and enclosures for grounding electrode conductors must be electrically continuous from the point of attachment to cabinets, equipment, to the grounding electrode, and must be securely fastened to the ground clamp or fitting. This requirement is found in Article 250.64E. Continuing with requirements for grounding electrode conductor installation, they are not permitted to be smaller than the neutral conductor or the largest conductor. The grounding electrode conductor is not required to be larger than 250 kc mil aluminum or 3/0 copper. And where connected to a rod, pipe, or plate electrode, the grounding electrode conductor size is not required to be larger than number 6 AWG aluminum or number 4 AWG copper. This is identified in Article 250.64B. Additionally, a ground fault circuit conductor is required to be brought to the service equipment. This is identified in Article 250.186. Continuing with grounding electrode conductor installation, there's a couple of new amendments to the 2019 edition of the California Electrical Code, and they are the following. Number 1, hold-down bolts connected to structural steel columns are permitted for connection to concrete encased electrodes. This is identified in Article 250.68 C2. Also, rebar is permitted to be used to connect concrete encased electrodes to bonding jumpers in accessible locations. This is verified in Article 250.68C3. Remember that Table 250.122, which is titled Minimum Size Equipment Ground Conductors for Grounding Raceway and Equipment, identifies the required size of grounding electrode conductors for equipment. But also remember that tables are for reference only. The designers will have already used them for determining the design, so it's critical that project inspectors inspect electrical installations of all components electrically, including grounding electrode conductors and grounding electrode systems based on the approved plans. This picture on the right-hand side of this slide shows an example of a grounding electrode conductor which was not properly terminated and torqued as is required per the installation instructions. Articles 110.3b and 110.14a address this in more detail. We're now going to begin discussing bonding installations. It's important that project inspectors verify and identify proper bonding installations. This information is also located in Article 250, but in Part 5. Metal parts of service equipment must be bonded together, as is verified in Article 250.92. Additionally, communication systems bonding must use one of the following: either an inter-system bonding termination device, which is basically required to reduce electrical noise, or aluminum or copper bus bar, measuring 1/4 inch minimum in thickness by 6 inch minimum width by a sufficient length. And that sufficient length, again, is going to be determined by the electrical engineer that has designed and approved the electrical plans. Bonding for over 250 volts to ground around concentric, eccentric, and oversized knockouts is required per Article 250.97. Continuing with verifying proper bonding installations, all metal piping systems, water and gas, and any exposed structural steel must be bonded. This is required per Article 250.104. Supply side bonding must be sized per Table 250.66. This is required per Article 250.102C. But again, project inspectors are cautioned to use these tables as a reference. These are used by design professionals in the design of the electrical systems on the project, and the plans must be used as the reference material to inspect from. Bonding jumpers are permitted to be aluminum, copper, copper-clad aluminum, or other corrosion-resistant material per Article 250.102A. Generally speaking, the bonding jumpers must be wire, a bus, a screw, or other suitable conductor. Continuing with requirements for bonding jumpers, the installation of bonding jumpers must be protected in accordance with the grounding electrode conductor installation requirements found in Article 250.102E3. Aluminum and copper-clad aluminum are not permitted to be in direct contact with the earth, masonry, or other corrosive environments, and where used outside, they are not permitted within 18 inches of the earth. These are both similar to the grounding electrode conductor installation requirements and are reiterated here for clarity. Bonding jumpers are also permitted to be installed on or through framing members. These two photographs show a couple of examples of bonding bushings, and non-bonding bushings. The photograph on the left shows a bonding bushing. The photo on the right shows a situation where a bonding bushing is required, but it is not installed around the concentric knockout per Article 250.97. These photographs show a view of a water pipe with a bonding clamp attached to it that is improperly sized for the conductor. I know it's difficult to see, and we attempted to blow up the view, but it's very important that project inspectors understand that they must check all of these bonding clamps to make sure that they are approved for the size bonding conductor that is being used. These two photographs show a couple of examples of an improper installation for a bonding conductor on the left-hand side and the corrected proper installation of the same bonding conductor. Remember that we discussed previously that Article 250.64e states ferrous metal raceways and enclosures for grounding electrode conductors must be electrically continuous from the point of attachment to cabinets or equipment to the grounding electrode and must be securely fastened to the ground clamp or fitting. As you can see in this photo on the right hand side, this particular raceway has been clamped to the grounding electrode conductor or the bond itself, and the improper installation, the actual grounding electrode conductor or the bond wire, is not really positively attached. It's just laying on the opening of this conduit. Unacceptable. Now we're going to talk about equipment grounding. And this particular topic of equipment grounding is discussed in Article 250, Part 6. Types of equipment grounding conductors are addressed in Article 250.118. And it basically says copper, aluminum, or copper-clad aluminum conductors, either stranded, solid, insulated, covered, or bare, wire or bus bar of any shape, are permitted to use as equipment grounding conductors. Rigid metal conduit, intermediate metal conduit, electrical metal tubing, including flexible metallic conduit, liquid tight flexible metallic conduit, flexible metallic tubing, armored cable, mineral insulated metal sheathed cable, which we hardly ever see, and metal clad cable are acceptable too, but all have restrictions. Additionally, cable trays, cable bus framework, and other listed metal raceways and auxiliary gutters, including surface metal raceways, which are listed for grounding, are acceptable for use as equipment grounding. Continuing with equipment grounding, it's important that identification of equipment grounding complies with Article 250.119. Specifically, conductors number 6 AWG and smaller must have green insulation. Larger than 6 AWG may be identified with green tape at terminations. The size of equipment grounding conductors is addressed in Article 250.122 and Table 250.122. Where ungrounded conductors are increased in size, the equipment grounding conductors must be proportionally increased in size. And where conductors are installed in parallel, equipment grounding conductors must be installed full size in each raceway or cable. The details for connections and attachments of equipment grounding conductors to boxes is identified in Article 250.148. Splices and terminations are required to be identified for the use. The removal of a receptacle, luminaire, or other device must not interrupt the equipment grounding continuity. Specifically, we see pigtails typically used in order to make sure that this type of situation never occurs. The connection to the box must be made by a grounding screw or another listed grounding device which is used for no other purpose. The photo on the right-hand side of this slide illustrates a situation where one grounding lug termination is being used. However, it's not listed for multiple conductors. This is identified in Article 110.14a, and this is another thing that project inspectors need to be on the lookout for. The photograph on the left-hand side of this slide depicts a situation where a contractor involved in a retrofit discovered that a previous contractor incorrectly re-identified a couple of conductors with tape. Now these two conductors that are pointed out with arrows here, one being white and the other one green, have actually had white tape and green tape applied to them respectively. Both of these conductors are smaller than 6 AWG in size and are therefore required to have colored insulation. If they were larger than 6 AWG, then they would be permitted to be taped the corresponding color. However, this particular installation is not permitted and does not comply with code, and this is the type of thing that we definitely don't want to see, and that project inspectors should remain ever vigilant for, especially in retrofit type projects. This information is reiterated in Articles 260 and 250.119. Now we'll talk a little bit about equipment anchorage and bracing. It's important to refer to the manufacturer's installation, bracing, and support requirements for all components. This is reiterated in Article 110.3b. Project inspectors must verify construction document requirements for bracing and support of electrical equipment. It's important to refer to the 2019 California Building Code for additional seismic requirements, and remember that any changes from the DSA approved plans may require DSA review and approval via a construction change document, or CCD. And again, it's important to remember that only the district structural engineer can compel the design team to issue a CCD. We're going to take this opportunity to reiterate a very important issue that we have addressed previously in both the mechanical and the plumbing presentations, and that is that hanger, bracing, and support information is required to be on the DSA approved construction documents. This is required per the California Administrative Code, Section 4-317B. The plan sheet notes may indicate details will be provided. However, if this information is not provided by the design team during plan review and approval, a CCD is required. And another reminder that only the DSE, or the District Structural Engineer, can compel CCD submission. So, wise words to the project inspector are this: do not attempt to inspect hanger and support installations from other reference publications. The project inspector must be able to verify hanger, bracing, and support of all electrical elements in accordance with the approved plans. The project plans must specify the details for all electrical component hanging, bracing, and anchorage. And that is the document that the project inspector is compelled to inspect from for compliance. Whenever a contractor is drilling for any anchor, There's some important considerations for everyone to keep in mind. Number one, is there pre or post-tension concerns in concrete substrates? It's very important to not drill into any structural element, whether it's rebar, tendons, embeds, etc. It's important that the contractor follows the manufacturer's installation instructions, including the installation torque for any torque-controlled anchors. It's also important to review the contract documents for required anchorage pull testing and special inspection requirements. And this is going to be found on the form DSA 103, which is the listing of required structural tests and special inspections. This image shows a nice, clean installation of some electrical trapezing, which is supporting a cable tray. And as you can see closely here, this particular setup includes a seismic brace as well as a hanger assembly. And again, this type of installation is certainly going to be reviewed and approved by DSA plan review staff prior to approving the plans for construction.